Okay, let's work on another example. Here is another problem. Let alpha, beta, gamma be the complex roots of the polynomial x cubed minus 2. There are three such roots, I just call them alpha, beta, gamma. Find the degree of this extension where I join all the roots, all the three roots to q over q. So first of all, let's compute these roots. Let's identify what they are. You know very well how to factor this polynomial. So the roots are cube root of 2, cube root of 2 zeta 3, and cube root of 2 zeta 3 squared, where zeta 3 is cosine 2 pi over 3 plus I sine 2 pi over 3. So what I can do is I can draw this diagram where I join each root one root at a time. And I denote these degrees by D, E, and F. And by the Dedekind product theorem, I know that the total degree is going to be the product, D, E, F. So that means I have to compute each of these degrees. So first of all, the degree D is 3. Why is it 3? Because I already know the degree of the minimal polynomial of cube root of 2 over q is 3. It's x cubed minus 2. This actually is the minimal polynomial of cube root of 2 over q. So now E. So I need to know what is the degree of the minimal polynomial of cube root of 2 zeta 3 over q adjoint cube root of 2. Well, so I look at the polynomial x cubed minus 2 and I look at its factorization, and first of all I see that I can factor it this way. And now I check that actually both of these polynomials here have coefficients in q adjoint cube root of 2. Both of these polynomials, right? All the coefficients lie inside the field q adjoint cube root of 2. So I'm adjoining this root to the field q adjoint cube root of 2. So I know this is a root also of this polynomial. So I'd like to know it is a root of which of these two factors. Where it cannot be the root of the first factor because I know the root of the first factor. That's just cube root of 2. So it must be the root of the second factor. So that means that this degree, that this E is at most 2. So as we get that it is at most 2. So what are the options for E? Either 2 or 1. Why can't E be 1? If you wish, you can pause the video again here and think about why E couldn't be 1. So now let's answer this question. So if E were 1, then these two fields would be the same. But that would mean that cube root of 2 zeta 3 is an element of this field. But this field is completely contained inside the real numbers, and this isn't. So contradiction. So E is 2. Okay, this gives us the value of E. So the last thing is to determine the value of F. And I actually claim that F is 1. That once you have adjoined two roots of this polynomial, the third root is already there. So I'll claim F is equal to 1. So to show this, it is enough to show that the remaining root, this one here, belongs to the field this field over here. So that means I have to be able to express this by these two guys. So how do I do that? First of all, well, I would like to just say, oh yeah, well, this thing here is just that times zeta 3 squared. But a priori, I do not see that zeta 3 belongs to this field. What I know is that cube root of 2 belongs there, and cube root of 2 zeta 3. I do not have zeta 3 by itself there. Or do I? So note that I can write zeta 3 as cube root of 2 zeta 3 divided by cube root of 2. Now note both of these elements, this and that, are in this field. And because it's a field, I can divide. So I can write the ratio. The ratio is also in that field, so zeta 3 is in that field. Well, hence we're done. Because once I know that zeta 3 is here, and I also know that cube root of 2 is here, then this thing is also there, because in a field I can definitely multiply. So F is 1. So conclusion. This degree is 6. So when you adjoin all the roots of this polynomial x cubed minus 2, you get an extension of degree 6. So let's move on to an example about factorization. And the question is the following. 3 factor the polynomial x to the 4th minus 2x cubed minus 7x plus 14 into irreducible factors over Q and other fields and some other fields. Okay, I'm gonna tell you what fields I have in mind here, what fields I want you to factor it over as we move on. So first of all, factorization over Q. So over Q. If you look at this, I can actually group terms here. So I can take out x cubed from the first two terms and then minus 7 from the next two, and I get this factorization. And I claim these factors are irreducible over Q. Why is that? Because the first factor has degree 1 and every degree 1 polynomial is irreducible, and the second factor is cubic and it does not have any roots in Q. I know its roots are cube root of 7, and 7 is not a perfect cube, and then the other two roots are not real, so they are irreducible. Let's do a factorization over the reals. Well, in this case, I can factor this last factor further, and I get x minus cube root of 7 times x squared plus cube root of 7 x plus cube root of 7 squared. So I again claim these factors are irreducible over R this time. The first two because they're degree 1, and the last one I know its roots. Its roots are the remaining two non-real roots of x cubed minus 7, so they're non-real. So because the polynomial is quadratic and it does not have any real roots, it is irreducible. Let's do factorization over C. In this case, I can factor this last polynomial even further. And every factor is irreducible over C because they are degree 1. Okay, but there are also other fields you can consider factorization over. For example, you may ask, what's the factorization over Q adjoin cube root of 7? Maybe I already have that factorization on the board. Well, certainly both of these polynomials have coefficients in Q, so they have coefficients in Q adjoint cube root of 7. But are they irreducible over Q adjoint cube root of 7? The first one is, because it's degree 1, but the second one, well, I would like to know that it has no roots in Q adjoint cube root of 7, but it does have roots there, because one of its roots is cube root of 7. So that means this factor also has coefficients in Q adjoin cube root of 7. So I already know that this thing actually factors over Q adjoin cube root of 7 into this times that. Look, right, all the factors here, all the coefficients are actually lie in this field. So is this factorization then a factorization into irreducibles over Q adjoint cube root of 7? Well, these two are now irreducible because they are degree 1. What about the last one? I know the roots of the last factor. They are cube root of 7 zeta 3 and cube root of 7 zeta 3 squared, and none of these are real, right? And this field is contained inside the real numbers. So that means this thing actually does not have any roots in Q adjoint cube root of 7. Because again, its roots are non-real, and Q adjoint cube root of 7 is contained in the real numbers. So that means it's also so this polynomial is irreducible over Q adjoint cube root of 7. So this factorization is actually valid also over this field. What about the following field? Where I join both cube root of 7 and zeta 3. Well, in this case, actually, all the roots of this factor lie in this field, right? Because I know what the roots are. They are cube root of 7, cube root of 7 zeta 3, and cube root of 7 zeta 3, squared. And all three lie in this field. They can be expressed by cube root of 7 and zeta 3. So that means the polynomial f of x factors completely into linear factors over that field. So this factorization here is also valid over cube root of 7 zeta 3. Let's look at yet another possibility. What about over the following field? Note, this is different from this situation. Here I put in a comma, which means both cube root of 7 and zeta 3 are in this field. Here there is a times between them, so that's just Q adjoin one particular number, cube root of 7 zeta 3. So I look at this factorization and I see that this guy actually lies in that field. So I can definitely factor. So I can write f of x as x minus 2, then x minus cube root of 7 zeta 3. Okay? But I'm sort of wondering, so do also the other two roots lie in that field? Right? So the two other roots that I haven't yet accounted for are this and that. So does cube root of 7, so question, does cube root of 7 also belong to this field? I can't immediately say, oh no, because like this isn't real and this is contained inside the real numbers. No, because in this case actually this is real and this actually is not contained inside the real numbers. So it is possible for a real number to lie in some field that has also some non-real numbers in it. But look at this. Suppose it is. So if so, then I have this containment of fields. So I have the following tower, Q adjoint cube root of 7, and Q adjoint cube root of 7 zeta cubed. The degree here is 3. What's the degree here all the way to the top? Well, I would need to know what's the minimal polynomial of this complex number over Q. But I know a polynomial that has this as a root and has coefficients in Q. That's namely x cubed minus 7. Right? This thing is also a root of x cubed minus 7. And x cubed minus 7 is irreducible over Q. I already know that. So this is also 3. So because the minimal polynomial of cube root of 7 zeta 3 over Q is x cubed minus 7. So this is also 3. Oh, if that's also 3, then this E has to be 1. So these two fields are equal. And now I can use this trick by saying, well, that's not possible because that's contained inside the real numbers and this one isn't. So contradiction. Okay? So that shows me that the answer here is no. This contradiction shows that the answer here is no. Cube root of 7 does not lie that. Which means whatever I get from multiplying these two polynomials, so this factor is not there. So whatever I get from multiplying these two polynomials must be irreducible. So what is it that I get? So this is x squared minus cube root of 7 zeta 3 plus cube root of 7 plus cube root of 7 zeta 3 squared. Oh, sorry, there's an x, and this is irreducible over Q. Adjoint cube root of 7 zeta 3. Now, if you follow this closely, you might become suspicious because the polynomial doesn't look like it has coefficients in this field. That is, okay, this coefficient surely lies here, but what about this? It does seem like it has a cube root of 7 in it. So why is this actually an element of this field? So I'll leave it to you here as an exercise. Sort of a challenge. Show that cube root of 7 zeta 3 plus cube root of 7 is actually in this field. Now, I actually do not need that challenge to say that this polynomial has coefficients in this field because I know that if I multiply these two polynomials, I get x cubed minus 7. Okay, and x cubed minus 7 has coefficients in this field for sure because it has coefficients in the rationals. And I know that this polynomial has coefficients in q adjoin cube root of 7 zeta 3. And this polynomial I just get by dividing this one by that one. So it automatically must have the coefficients in the right field. It's just that when I write it this way, it's not sort of immediately obvious for the eye that the coefficients lie there. They must, but if you wish to actually rewrite it in a different way so that it's clear that it sort of looks like this, then it looks like elements of this, then I give you this challenge. Okay, and the last question, what's the factorization of this polynomial over q adjoin radical 2? Okay, so let's start out again with my f of x. Its factorization over q was like this. So the question is, maybe this is already also irreducible over q adjoin radical 2. So is this clear or not? Well, if this were reducible over q adjoin radical 2, if x cubed minus 7 was reducible over q adjoin radical 2, then it would have a root. Then it would have a root in q adjoin radical 2 because it's a cubic polynomial, and I know its roots. The cube root of 7, cube root of 7 zeta 3, and cube root of 7 zeta 3 squared. Only one of them is real, and this field is definitely contained inside the real numbers. So the only root that has a chance of being inside q adjoin radical 2 is cube root of 7. So q adjoin cube root of 7 would be a subfield of q adjoin square root of 2. Oh, but that's not possible, right? Because that's a three-dimensional vector space over q, while the other one is just two-dimensional vector space over q, and a three-dimensional space cannot sit in a two-dimensional space. So, not possible. As three-dimensional space cannot sit in a two-dimensional space. So x cubed minus 7 is irreducible. Over q adjoin radical 2. So then, as a conclusion, I get that this is the factorization into irreducibles over q adjoin radical 2. In fact, let me just give you, actually no, I think that's probably good enough. If you look at the homework, you have a lot more examples of this type. Most of them are actually easier than this particular problem.